After more than 2 decades of intensive study, research into climate change offers an encouraging reality. In 1990, early studies of climate change suggested that carbon dioxide from fossil fuels was causing global warming and it could lead to disaster. Now, 25 years later, studies of climate change reveal an encouraging reality. The climate is changing, it's indisputable. Many think it is warming, although exactly where is an open question. Is it in the atmosphere, or on the land, in the oceans, or is it all three? The amount of carbon dioxide in the atmosphere is going up. An observatory in Hawaii has been recording the increase. There are precise measurements since 1960, and a very good estimate of the increase since we began using fossil fuels. Graphs from 1990 show that atmospheric carbon dioxide is increasing and annual average surface temperatures are trending upward. And this begs the question, is the increase in carbon dioxide changing the climate? Over a century ago, physicists Arrhenius and others thought that more CO2 might raise temperatures. They coined the term the greenhouse effect. Interest rose in the 1950s when oceanographers learned that new measurements showed that the amount of carbon dioxide was going up. To determine the effect of carbon dioxide, the scientific method called for hypotheses to be tested. The 3 possible relationships are shown here. But we can't put the planet in a test tube and conduct experiments. To start studying the climate, it was logical that meteorologists should take the lead. To make weather forecasts, they use models of the atmosphere. Models take many forms. An aquarium is a model of the ocean. A schematic is a model of events. A planetarium is a model of the sky. But how well does a model represent reality? And how much reliance can we put on it, particularly one that tries to predict the future? Before computers, models were laid out on maps. The atmospheric conditions causing movement of weather systems were given the label forcing agents. With the advent of computers, higher resolution models made better forecasts. Decades ago, people made jokes about the weathermen, but not today. Data sets are used in weather models. After days of normal weather or after a major weather event, forecasters compare the model prediction with what happened, analyze the data, and make improvements in the model. We are familiar with hurricane track forecasts, which come from models. But unlike daily weather forecasts, which have improved after analyzing years of daily events, hurricane forecasts still have large cones of probable track paths. And different models often have very different track forecasts. Over the years, the models have gotten better. The track error, the difference between the predicted track and the actual track, has been reduced. For example, the track error 48 hours in the future averaged 200 nautical miles in 1990. In 2014, the error was less than 60 miles. This is partly because computers are better, but more importantly, there have been thousands of forecasts to compare with actual events, or, in other words, chances to compare the models with reality. Although hurricanes are big events, only a few factors affect the track a storm takes. We know where a storm is and where it went, but there has been little improvement in predicting the intensity of hurricanes. Intensity models are more complex. It is more difficult to measure a storm's energy, the heat engines that are driving it, and the influence of heat sources and sinks along its path. Many complex dynamics affect the intensity of a hurricane. Even after decades of hurricanes in the age of advancing computing power, intensity models have not improved. Compared to modeling hurricanes, modeling the Earth's climate requires dealing with many, many more and far more complex factors. Weather models cover small portions of the Earth's surface. Climate models try to capture the incredible complexity of the entire planet, its atmosphere, its land, its oceans, and the sun itself. And to further complicate things, of course, the Earth is in darkness and varying degrees of sunlight every 24 hours and at different angles to the sun each day of the year. But concern about carbon dioxide convinced researchers to press ahead and try to construct a global climate model, despite the tremendous challenges they faced. To coordinate the immense undertaking, 2 UN agencies created an intergovernmental panel on climate change, the IPCC, to bring together the best scientists and institutions to study climate change. After 2 years of work, the IPCC published their first report in 1990. Essentially assuming a direct correlation between carbon dioxide levels and global warming, the early models tried to quantify the temperature rise that would accompany growing levels of carbon dioxide. This first try suggested that average temperature would increase 0.2 to 0.5 degrees centigrade per decade. Some world leaders became alarmed and suggested that the worst-case prediction should drive policy, believing there could be severe consequences if temperature rose by 2.5 degrees by 2040, the worst case. Knowing that the sheer complexity of the climate made the early models a first guess, the IPCC decided to do more research and provide new assessments every 6 years. More data was acquired, the models were expanded, and new theories were proposed. But still, unlike hurricane models, there was no way to validate the model predictions. When the 5th assessment report was released in 2013, panel members were satisfied that there was a sufficient span of time, 60 years, and enough data sets across those years to identify with some confidence the actual rate of warming. Although the first report predicted a rise of between 1.2 and 3.0 degrees over 6 decades, the actual warming was reported as 0.64 degrees over 6 decades, about 0.1 per decade. The 5th assessment also published the amount of warming from 1850 to 2010, 0.85 degrees, or about 0.05 per decade. After years of dedicated and expensive research, why were the climate model predictions so wrong? In crafting the models, meteorologists first examined the dynamics of the atmosphere. Incoming solar radiation has an energy spectrum, shown by the yellow curve in the inset graphic, that is mostly visible light with some ultraviolet and shortwave infrared. About 30% of the sun's energy is reflected back into space. The rest is absorbed by the atmosphere or the Earth's surface. Unlike the superhot sun, the Earth's surface and atmosphere radiate heat energy as long-wave infrared, and 70% of the sun's energy is returned to space in this form. Reducing the complexity to simple heat transfer components, we see during the day that incoming solar energy heats the Earth and the atmosphere, and this heat is transferred from the Earth's surface by radiation, convection or air currents, and conduction, direct transfer of energy from molecule to molecule. At night, these modes continue to transfer heat from the surface through the lower atmosphere and out into space, and the atmosphere itself starts cooling, also transferring heat outward. Compared to the Earth's diameter, the atmosphere is a very thin layer. About 75% of all atmospheric gases are in the lowest 10 kilometers. These gases slow the transfer of heat out to space at night and spread heat around the globe, limiting summer and winter extremes. The most effective atmospheric gas in reducing heat transfer is water vapor. As this logarithmic graph shows, most of the water vapor is within 10 kilometers of the surface. There is much more of it than all the other infrared-absorbing gases combined. Also, water vapor can condense into clouds, serving to trap air currents and limit the loss of heat by conduction. Water vapor's strong influence is why arid regions like Death Valley have much wider day-to-night temperature swings than tropical humid regions like Florida. Water vapor and clouds slow heat transfer. To start making climate models, meteorologists looked at what engineers knew about the properties of carbon dioxide to affect heat transfer. Handbooks and experiments showed that emissivity, a measure of absorbing heat, was related to the density of carbon dioxide. Some thought that more carbon dioxide in the atmosphere would have a significant heating capacity, trapping heat instead of allowing it to dissipate into space. In a leap that became embedded in climate models, more carbon dioxide in the atmosphere was assumed to be the cause of more warming. The IPCC gave this idea a name, the radiative forcing concept. This drawing, typical of many that depict the greenhouse effect, illustrates the way infrared absorbing gases affect heat transfer in the atmosphere. Overly simplistically, these gases are represented as a layer that reflects infrared radiation back down to Earth. The theory of radiative forcing is that increased levels of CO2 and other infrared absorbing gases heat the atmosphere, reduce heat transfer to space, and therefore trap more heat and raise the Earth's temperature. Physicists have proven that an object emits infrared radiation along a spectrum of wavelengths. If the Earth was at 20 degrees centigrade, it would emit the spectrum shown by the red curve. Molecules of the gases in the atmosphere interact with the waves by absorbing the photons and then re-emitting them. The absorption spectrum of the mix of gases is the light blue curve. How does carbon dioxide's property of emissivity affect heat transfer in the atmosphere? This shows two slices of air. Each is 1 molecule thick and measures 250 by 100 molecules, a total of 25,000 molecules. The slice on the left shows CO2 at 280 parts per million, the level in the year 1750. The slice on the right is at today's level of 400. The CO2 molecules are shown as white dots, as much to scale as possible. Here, the CO2 molecules are highlighted with squares to make them more visible. It seems logical to ask, can such a tiny change in the number of molecules make a difference? This is a typical depiction of radiative forcing. It shows that doubling the amount of CO2 will result in more heat from the Earth being reflected downward. Notice how most up arrows that hit a molecule result in down arrows, implying reflection. Let's examine this more closely. This is another slice of air molecules. The blue dots represent CO2, while all the empty space is filled with other atmospheric gas molecules, mostly nitrogen and oxygen, which don't absorb long-wave infrared. The white arrows represent a photon of infrared radiation leaving the surface. Most don't get near a CO2 molecule. If one does collide with a CO2, it might be absorbed, and if it is, the overexcited molecule will emit a similar photon. In other words, the CO2 acts to scatter the photons. We see here two collisions, with the re-emitted or scattered photons shown in light green. The photons continue to travel in a straight line from the source that emitted them. In each photon to CO2 interaction, the new photon is not reflected backward like bouncing a ball against a wall, but in any direction, like any of the sparkles in a starburst firework in the night sky. A re-emitted photon can strike another CO2 molecule, resulting in a second-generation photon, shown here in yellow. And for this little exercise, we conclude with this array of photons. CO2 mixed into the air does interact with outgoing radiation, but it doesn't significantly inhibit the outward spherical spreading of the infrared radiation. Here we have added molecules of water vapor. This drawing significantly underrepresents the number of H2O molecules, but the point is that in the lower atmosphere, infrared scattering is dominated by water vapor, and the total flux is away from the Earth's surface. In the atmosphere below 10 kilometers, water vapor is the driving influence not only on radiated heat transfer, but also on convection and conduction. It is only above 15 kilometers that other infrared scattering gases start to play a significant role. So, above 15 kilometers, what is the significance of CO2 in scattering infrared energy or affecting heat transfer? As explained earlier, the sun heats the atmosphere and the Earth's surface by day, and at night, the surface and the atmosphere begin to cool by radiating heat back into space. These curves show how sunlight raises atmospheric temperatures versus altitude. The solid line for the tropics and the dashed line for winter mid-latitudes. Below 15 kilometers, the heating rate rises rapidly where increasingly dense water vapor absorbs the sun's energy. Above 15 kilometers, the rate also increases where ozone absorbs the energy of the sun's ultraviolet rays, warming the atmosphere and reducing harmful ultraviolet radiation on Earth. At night, the atmosphere radiates heat outward and cools down. The greatest cooling is near the surface and above 15 kilometers. The solid line is the total cooling from infrared emitting gases. Also shown here is the partial contribution of water vapor, ozone, and carbon dioxide. Below 10 kilometers, H2O drives atmospheric cooling. The three curves represent the three bands of radiation which water vapor reacts to in different ways through separate photon-to-molecule interactions. There is a cooling contribution from carbon dioxide, but it is a weak contributor. Still, note that at night, carbon dioxide is not reflecting heat either into the atmosphere or onto the Earth's surface. It is radiating heat outward. Above 15 kilometers, water vapor has no effect on cooling. Above 27 kilometers, there is rapid cooling as a result of infrared radiation emissions from ozone and carbon dioxide that were heated during the day. Between 15 and 27 kilometers, there is actually some warming. Carbon dioxide causes the atmosphere to warm slightly between 15 and 16 kilometers, and ozone even more warming over a greater height from 15 to 30 kilometers. The warming in this region makes sense. The coldest layer of the atmosphere is between 10 and 20 kilometers. It is bounded above and below by warmer air, and heat naturally flows from warm to cold. Still, in this narrow layer where carbon dioxide causes warming, couldn't an increase in the amount of carbon dioxide cause additional heating? Carbon dioxide's density in this layer is inconsequential. Taking together all of the thermodynamics of the atmosphere, combined with the known physical properties of carbon dioxide, this layer does not have any significant effect. 50 years ago, erring on the side of utmost caution, some believed that CO2 could dangerously affect the Earth's climate. The IPCC was created to examine possible scenarios. But after decades, the IPCC's models have proven exaggerated, with warming at half the lowest predicted level. And a growing number of climate researchers believe that the IPCC's temperature data sets are inaccurate and that there has been less warming. The climate is an incredibly complex system. It is heated and cooled every 24 hours, and the atmosphere and oceans are swirling dynamic engines of heat transfer. Models may eventually capture all the complexity, but as hurricane models illustrate, it is only after the models can be validated by actual events that we can have any assurance that the models are accurate. Planet Earth has been on a journey of continuous change. With advances in technology, we are gaining a better understanding of what affects that journey. Yet the more we study planetary dynamics, the more sensors we deploy, and the more data we collect, the more we are realizing the incredible complexity of the Earth's climate and that climatology can't be simply an extension of meteorology. Oil and gas are precious resources. There are many good reasons to conserve them by improving efficiency and expanding the use of alternatives. But concern about the carbon dioxide generated by using these resources is not among the reasons. The climate changes. There are so many things affecting it that it's impossible for it to be static. Today, the predictions coming from what's called climate science are in fact little more than calculations made by computer models. The models are incapable of capturing the Earth's infinite complexity. The models cannot be validated. The models rely on a concept, radiative forcing, that is in conflict with physics and thermodynamics. Rising levels of CO2 are not forcing planetary changes. Earth, in fact, is an amazing and resilient planet. Its ecosystem is able to evolve, and human beings can adapt. The recent climate trend is warmer air and water, which is accompanied by rising sea levels. This will require human beings to make modifications. Three main impacts will need to be addressed. Along the coasts, lands will be flooded. In some regions, there may be changes to the ecosystem, one being growth of deserts. And agricultural practices are dependent on the climate. The Earth and its inhabitants have adapted to warm and cold climates since before recorded history. An ice age around 1700 BC allowed for migration across ice bridges connecting Asia to the Americas. Civilizations advanced in warm periods. Even in ancient and medieval times, mankind has adjusted to change. The Little Ice Age spawned severe winters and cooler summers as recently as the 1600s and 1700s. Warming since that time has not been catastrophic. In fact, it has made life more comfortable. We'll have to adapt to rising sea level. The Dutch have lived for years in a country of dikes and windmills that were built to pump water. Years ago, they built a barrier across the mouth of the Zuider Zee, turning it into a freshwater lake and reclaiming land, shown in green on the graphic. Venice, Italy, is building a barrier to stop high tides that were frequently flooding the sinking city. These people didn't just surrender to rising sea levels. They engineered ways to adapt. Desertification may increase, such as the growth of the Sahara. Lakes may dry up, as has happened to Lake Chad. China has launched a green project to limit expansion of the Gobi Desert. We are learning how to exploit deserts, for example, by installing solar panels or piping in water for farming. The UN has a convention to address spreading deserts. Agricultural practices can be modified. Growing seasons have gotten longer, and some believe the present warming trends will lead to higher yields. Plants and animals will adapt in their own way, as they have for centuries. One area of great concern is endangered species. Another UN convention is working on this, as are many wildlife groups. But here we see an example of how decades of wayward models have led to nonsensical claims that fossil fuels are endangering species. This is disingenuous and diverts resources from effective conservation efforts. Climate change will undoubtedly impact the ecosystem. We need to focus on what will change and how it will change, and reject the counterproductive idea that everything will get worse. Legislation in the late 1980s created the U.S. Global Change Research Program. It collects data and makes predictions based, again, on models. Here are the key messages from its National Climate Assessment. Their models indicate there is little hope. Everything except growing seasons will get worse. Climate change will be unhealthy, they claim. More disease, sickness, even plagues. Despite longer growing seasons, their models say crop yields will decline. Their models reveal that climate change itself has a mortality threshold that will kill forests. Despite the real trends in rising sea levels, their climate models predict frightening future levels. Regrettably, for decades, school children have been taught that science proves that disastrous climate change is coming and that it is a result of using oil and gas. Here is just one website directed at children. Let's listen to what Tiki the Penguin has written.
You've probably heard about the greenhouse effect. If you walk into a greenhouse on a sunny day, it's very warm inside because the sun's heat is trapped by the glass. Carbon dioxide gas pumped into the air by burning fuels has just the same effect. It traps the sun's heat energy near the surface of the earth, making the air and oceans warmer. This is what scientists call climate change or global warming. The earth is warmer than it should be, so the seas and oceans take up more space because warmer water expands. The warming is also making icy places like the Arctic and my home, the Antarctic, melt away. Lots of my penguin friends are dying because of this and because of pollution. The melted ice drains into the oceans, making sea levels rise even more. Warming means that the level of the sea goes up everywhere, causing lots of floods. Warming also means more unpleasant weather, with more and bigger hurricanes, typhoons, tornadoes, and cyclones. That means lots of people will get killed or go hungry because their land is flooded, washed away, or their crops spoiled. Other places will get hot and dry as people cut down more and more forests. I don't want to see these things happening, and I don't suppose you do either. So what can we do?
The climate is changing. It always has, and it always will. The 2006 movie An Inconvenient Truth ends with this narration. Quote, "Each one of us is a cause of global warming, but each one of us can make choices to change that. We can make choices to bring our individual carbon emissions to zero." End quote. That is simply wrong. The idea that climate change can be modified by lowering carbon emissions has misdirected our efforts, diverted our energy and resources in the wrong directions. And it is time to stop frightening our young ones with scary images and stories that misrepresent reality. As Franklin Roosevelt famously said, "The only thing we have to fear is fear itself." Those who advocate man-made global warming may be well-intentioned, but they are peddling fear instead of offering reason. And we have seen how their fear campaign has saturated the media and infected the thinking of our children. The time has come to take a new approach. The encouraging reality is that, although the climate is changing, we can handle the change.